We happy to have Eugene Gorsky from UC Davis, and he will speak about algebraic weaves and braid varieties. Lina, could you please post? Yeah, and whoever is responsible for the recording. Okay, let's start. So, Zhenya, please.
All right. So yeah, thank you so much for invitation. So I wish I could visit Kansas sometime in person. So I will speak about braid varieties. It's kind of new class of algebraic varieties. So I'll definitely define what these are and how to work with them and how they're related to some kind of more classical varieties and the varieties that you might know, and just give some concrete examples. And all this is a joint work with Jose Simental, who is now in Bonn, my brother Mikhail Gorsky, who is in Gien in France, and then Roger Casals, who is also professor in UC Davis. And all this is in two papers, one from 2020, another from 2021. They're both on archive, and there is more work in progress coming up. Okay, so what is a braid variety? So if I'm looking at n by n matrices and given a number I, and I is any number between n1 and n minus 1. So I can just look at this matrix. It's diagonal matrix with all ones except for the 2 by 2 block with 0, 1, 1, z. And this 2 by 2 block is at positions I and I plus 1. So this is right on the diagonal. And so this is just a matrix depending on one parameter. And we will need some information about the braid group. So just some background. So the braid group has generators sigma 1 through sigma n minus 1. The relations are here. So sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1, sigma I, sigma j, sigma I. If I and JF are apart. And again, like classically, so what is sigma I? You have a braid where you have a bunch of strands, then you cross I's and I plus first, and then you have a bunch of identity strands. So this would be sigma I, and sigma I inverse is the inverse, but we won't need the inverses. So throughout the talk, we just talk about positive braids. And positive braids means just products of sigmas with no inverses. So this is a monoid inside the braid group. So given such a positive braid, sigma I1 up to sigma ik, I want to define a big matrix, which will depend on, so if I have k different generators here, I will have k different variables. And I just take the first, this n by n matrix with index I1, with this 2 by 2 block at positions I1, I1 plus 1, depending on the variable z1, and so on. And then the last will be bik of zk. And just multiply all these matrices. It will be giant n by n matrix with complicated entries, depending on all these d's. But the entries will be some polynomials in zy through dk. And somehow one reason why this is not so bad is that these matrices satisfy the following relations. So bi of z1, bi plus 1 of z2, bi of z3, is actually the product of bi plus 1, bi, and bi plus 1 with slight change of variables. So here I put z3 in front, then z1 goes to the last one, and then in the middle I have some change. So instead of z2, I write z2 minus z1, z3. But the product of these matrices is equal to the product of these matrices. Again, you need to change variables, but after the change of variables, this is exactly the same as the braid relation over here. And if you have two matrices and I and JF are apart, it's clear that they commute because the 2 by 2 blocks don't interact. Okay.
So what's kind of the origin of this these BIs? It's what? It's coordinate on the one-dimensional Schubert cell in the flag variety. What does it parameterize?
Yes. You can say that this is this open Schubert cell in the flag variety, or kind of open Bra cell if you want, in this flag variety. So it corresponds to a pair of flags. Maybe that I should actually write down. Where should I write it down? I'll talk a little bit about this later, but I can say it now, maybe here. Sorry, need a bit more space. So I'm saying that I have a flag F and another flag F prime, and I can parameterize this flag by choosing some bases in all the subspaces. And here I choose another basis, and then basically I relate them by BI. So I think I want that F is BI of Z times F prime. So meaning that like I parameterize the flag by a matrix where the columns of the matrix span the flag. And then I think I do it correctly, or you take BI inverse, and then this condition, what does it actually mean? It means that this flag, if I look at Fj, then it is equal to F prime J, where J is not equal to I and I plus 1. And then, oh, sorry, if J is not equal to I, and then Fi is not equal to F I prime. So you can just look at this collection of pairs of flags, F and F prime, so that, again, you have a full flag in n-dimensional space. So I have all these Fj's, there's j-dimensional subspace. And I require that all the subspaces except for one are equal. And then at that place, at j is equal to I, they're actually not equal. And so that is an open subset in product of two flags. It's an open subset in both Simonton variety if you want. And then you can check that this relation between flags translates to this matrix relating them. So in this sense, it's Schubert cell in the flag variety, but I really want to think about it as a pair of flags in this kind of transverse position rather than just one flag. And then this condition, again, you can phrase it in terms of flag, but maybe we won't need it right now. Okay?
Mm-hmm.
Okay. And so now we define the braid variety. So we just have this big matrix, which is the product of the small matrices. And so for the big matrix, sorry, let me write it down too. Okay, I won't even try to change color right now. So anyway, so you can think of it, so this product of matrices is collection of flags. So I have some flag here, then I have some another flag here, another flag here, another flag here, and consecutive flags are related as I explained on the right. So this is, when I talk about this product of matrices, this is really a sequence of flags that you can think about. Anyway, if you don't like to think about flags, you just take this matrix for each I, and then plug in different variables. You have multiply all these matrices, it's a big matrix, and then in addition, you multiply it by W naught. So W naught is the longest element in symmetric group, or it's this matrix where I put ones on the opposite diagonal. Just the scalar matrix multiplied by this, and I require that the product is upper triangular. So this is a very, very concrete and I think easier thing than just thinking about flags. It's just like product of matrices times another matrix is upper triangular. And you look at all possible z's where this is satisfied. So this is clearly an affine algebraic variety in k-dimensional space where the coordinates are given by z1 through the k. And then we study this affine variety and its property. Okay, so maybe any questions at this point? So again,
the question probably I would have about the motivation. So it certainly look as intersection of two things in the flag variety or something like that. So it's some.
It's a sequence of flags. Again, we're looking for sequences of flags. Every two consecutive flags are related in this way.
I don't know. Can I to say it? This, for example, if I take,
I'll give an example in a second. Okay,
no, it depends. What do you call example? Maybe for me it will not be an example. If you so if you have, say, SLN,
Yeah.
you have a bunch of SL2 triples which can be embedded there. For you, it's not quite SL2 triples because the determinant of your 2 by 2 matrix, it's rather -1, but it's not a serious kind of restriction. So then the Z can be thought of as parameterizing the open cell in the like in CP1, which correspond to this SL2 triple. It's like open Schubert cell for SL2. So basically there is this classical kind of, I don't know, it's in the book of Steinberg, I believe, or whatever, that if you take this open two-dimensional, well, complex one-dimensional cells for SL2 triples, then if you take an arbitrary element in the while group, beta, then you can simply multiply these sets as a subset in SLN, and you get an element corresponding to this beta, and the result doesn't depend on the reduced decomposition.
Absolutely, absolutely. That's exactly what's going on here. So if beta is reduced, so if beta is just a positive lift of permutation, then what you said is absolutely correct. So you're saying that you have like as many parameters as the length of your while group element. And so this beta will be just always an element in the corresponding Schubert cell. And that's how you parameterize Schubert cell, basically. And then these parameters will give you coordinates on the Schubert cells. That's one way to parameterize. Yeah, I mean, there was slightly different phrasing in like Lucy old papers, but yeah. It's all the same. So this variety is not new for sure. Like, I mean, people studied it in like kind of many different names. But I mean, the main difference here, which is kind of less classical, is that so beta is not a permutation. Beta is really a braid, and it could be much longer and could be non-reduced, and that is like really important for us in this story. So you kind of do the same thing that you just described, but then like you allow beta to be arbitrary braid word, which could be very long. And we'll see examples like how this affects, like why this variety starts getting interesting topology and geometry and things like this. Okay, good. And yeah, as you said, so there's because of this fact, basically because of this identity on matrices, the variety does not depend on the choice of braid word, because if I choose the braid word I plus 1I or I plus 1I and I plus 1, the resultant product is the same after change of coordinates. So there's resulting algebraic varieties are also isomorphic up to change of coordinates corresponding to this. And so different braid words give isomorphic varieties. And in fact, canonically isomorphic, and I'll mention this towards the end. Okay.
And Misha, what kind of isomorphisms here when you say canonical isomorphism when you change the word?
So I'm saying that if I have X and I have some braid word and I have sigma I plus 1, sigma I, then this algebraic variety is isomorphic to the same thing for sigma I plus 1, sigma I, and sigma I plus 1. And the reason is exactly this fact and this identity, because you're like multiplying all the matrices, you do this change of variables, you go from Z1, Z2, Z3 to Z3, Z2 minus Z1, Z3, and Z1. But this is like algebraic isomorphism of affine algebraic varieties. So
my question is there a specific
I just give
expression of this isomorphism?
Yeah, this is
the corresponding to the braid relation.
Exactly. So any braid relation corresponds to an isomorphism. If I have two braid words which represent the same braid, they're related by a sequence of braid relations. And for each of them, you can do this isomorphism. And like canonical means that if I do it, it doesn't matter like which sequence of braid relations I take. And I'll mention this towards the end, like how do you actually prove this?
Will the relation between two different kind of presentations be somehow related to the homological tetrahedral equation?
Yes, we'll get there.
Okay, great.
Yeah.
So then
Yes.
probably it's all stuff somehow related to pos only groups. Okay. Mhm.
Yeah, maybe, but there will be some logical relation sure enough. Yes. Okay. Anyway, I just want to give an example. So before all this complicated things, so here's how this works. So you take the braid. Let's take 2 strands. Sigma 1 cube is the braid. So this is definitely non-reduced. So it doesn't fit into this kind of old classical framework, but it's really the same. So you have the matrices 0, 1, 1, Z1, that's sigma 1, that's sigma 1, that's sigma 1, and then I add an extra W naught by some technical reason. Multiply these matrices. Well, I don't want to read it, but that's what you get in the end. It's very explicit 2 by 2 matrix, and I require that this matrix is upper triangular, right? So this matrix is upper triangular if this thing is equal to 0. And so this is, we have 3 variables, Z1, Z2, Z3, and we have one equation that Z1 plus Z3 plus Z1, Z2, Z3 is equal to 0. And we want to understand this space, this affine algebraic variety. So one way to kind of visualize this space is to say that you factor out Z3 like this. So you're saying Z1 plus Z3 times 1 plus Z1, Z2 is equal to 0. And then we have 2 cases. So if 1 plus Z1, Z2 is equal to 0, then Z1 is equal to 0 from this equation. And that's actually impossible because like these 2 equations are incompatible. So that's a contradiction. If 1 plus Z1, Z2 is not equal to 0, then you can express Z3 as a function, as a rational function, negative Z1 over 1 plus Z1, Z2. And so you can just eliminate Z3. And so my variety, you can either think about it as a closed subset of C3 cut out by this explicit equation, or as an open subset of C2, where I just require that 1 plus Z1, Z2 is not equal to 0. And so what is this? Well, so this is kind of C2, and you subtract the quadric or hyperbole in some sense. And so this is a very, very explicit space. It will be kind of important later, but this is A1 cluster variety with one frozen variable, but we'll get back to this later.
Yeah, this is what I wanted to ask. But,
But
is it always cluster variety?
We'll get there.
Because it resembles, somehow I remember Sasha Goncharov told me, they had some paper with folk about this amalgamation of Poisson groups.
Anyway.
Yeah, all right. So maybe indeed.
Anyway, but like, I mean, just for reference, so like, I mean, if you know what cluster variety is, so you just draw the square, one cluster variable, one frozen variable. So this is type A1 because there's only one cluster variable. And this is this variety. And we'll talk like how this cluster structure actually appears geometrically in the end of the talk. Okay. But in any case, so any questions about this example, how I multiplied matrices, what happened here? I think that should be pretty clear.
And this example is the k equals 3 case, right? When k equals 2
k
in this
equals
example.
3. K equals 3 and n is equal to 2. That's right. So we should have just.
So what happens if k equals 2? Is that too trivial?
I think that's C star. I mean.
I see.
Yeah, you or
the Z1 equals 0.
Yeah, I think like what happens is that so you have this matrix times 0, 1, 1, 0, and I think you require that 1 plus Z1, Z2 is equal to 0.
Yes, you're right. You're right.
And so that is C star, and so that's it. Yeah. So yeah, it's easier. Like, I mean, this is the first interesting example which doesn't look like C star or C or something. And yeah. Okay. So what are the general properties of these varieties? So there are a lot of them. So let me list them all one by one. So the first is like when it is empty, when it is non-empty. So you could have asked what happens when k is equal to 2. You could have asked what happens if k is equal to 1 or even nothing. What happens for trivial braid? So for trivial braid, you have just W naught, and you want that to be upper triangular, but that never happens. And if your braid is somehow small or reduced, for example, then quite often this braid variety is just empty. This never happens that this matrix is upper triangular. And we have a criterion that this is non-empty if and only if the beta contains W naught as a subword. So you can take some subset of letters, subset of this braid generators, multiply them, and you get reduced expression for W naught, not necessarily consecutive. And you can rephrase it in various ways, but that's probably the easiest. So we know when it is empty, we know it's non-empty. And then if it is non-empty, we prove, and essentially this follows from the work of Laura Escobar. So I want to mention her here. So in her thesis, she considered very, very closely related varieties, and she proved that this is smooth of dimension, the length of beta, so this k, minus n choose 2, which is, of course, expected dimension because you have this many variables. Oops, I don't know what's the right thing. Okay, anyway. So this many variables, L of beta, and then you have n choose 2 equations, which say that everything below diagonal is equal to 0. And then the claim is that this is actually complete intersection, so it's smooth, and the dimension is the number of variables minus the number of equations. So that's good, and we definitely see that in this example it was smooth because it was an open subset in C2. Then you can ask, like, have we ever seen these varieties? And that's related to some of Jan's question. So in particular, some interesting examples, which we proved, are the following. So suppose that you have a pair of permutations, W and U, and W is bigger than U in Briard order on Sn. Then you can draw the following braid. So you take the positive braid lift of W, and then you take the positive braid lift of U inverse W naught by some reason. And then the claim is that this is an open Richardson variety for W and U.
So Richardson, it's intersection of positive and negative Briard.
Yeah, so this is intersection of the Schubert cell and the opposite Schubert cell. So Schubert cell for W and opposite Schubert cell for U. And somehow, I mean, if you follow this discussion about flag varieties and Schubert cell, what you explained, that's more or less automatic, that somehow you look at triples of flags, you have like a standard flag, another flag, and the W naught of standard flag, and then you want this middle guy to be in position W to the standard flag, in position U to the kind of anti-standard. And that's basically what this says. So this is maybe not so surprising, but in particular, you have all open Richardson varieties naturally embedded in this class. If W is so-called K-Grassmannian permutation, and still W is bigger than U, then there was a lot of work related to this Richardson varieties. Namely, this Richardson variety for W and U is isomorphic to so-called open positroid variety defined by Knudsen, Lam, and Speyer. And this is some subvariety of Grassmannian K-planes in n-dimensional space, which I'm not going to define. And then what we observed is that in this particular case, you can write it as 2 different braid varieties, actually like 4 different braids, which give the same braid variety. And in particular, you can just take this braid on n strands, it still works, but you can also take a braid on k strands, which is much more interesting, and get some other example. And I think we'll get to an example soon, but you'll see it. Okay, and so in particular, if you go back to this example, you can identify this with a positroid variety in Grassmannian G24. And I think I'll mention this later. So yeah, maybe let me write it down. So this is also a positroid, open positroid variety. In the Grassmannian of 2 planes in 4-dimensional space. And lots of people studied this varieties, starting from Knudsen, Lam, and Speyer. Okay, so we can get some interesting varieties, and this second part shows that actually in many different ways, you have different braids and different number of strands, but they can give you the same variety. And there are some other interesting varieties which appear this way, but this is kind of the most important class. which is still very rich. Okay, so what do we know kind of topologically or geometrically about these varieties now? So what can we get from topology? So topology tells us that first of all, we can count points in the braid variety over finite fields. So this is a very classical subject. And it turns out that the number of points in this variety is just the coefficient at the top power of a in the HOMFLY polynomial of the following link. So you take a braid beta, multiply by W0, and then take the braid closure. And so HOMFLY PD polynomial is some link invariant, which again, I'm not going to define. It depends on two variables, Q and A. And you just look at the top part, so the top power of A in this polynomial. And that's some polynomial in Q, and that agrees with the number of points over Q in this variety. And so in our kind of running example, so we have this variety. It's a plane minus hyperbola. 1 plus z1, z2 is not equal to 0. So how to count points? Well, you just have q squared, which is the number of points in C2 or whatever defined space. And then you subtract the number of points in hyperbola, but hyperbola is isomorphic to C star or GM, and then this is q minus 1. And so you get q squared minus q plus 1. And that agrees with the HOMFLY polynomial of the link. And in this case, the link is the Hopf link. Sorry, it is actually the closure of sigma 1 to the 4. So this is 2, 4 Torus link. And so if you like topology, you can say, well, take this link, compute its HOMFLY polynomial, take the top power of A, that gives you the number of points in this variety. This I will actually explain how to prove in a little while. This follows, I mean, if you like Hecke algebras, it follows from Hecke algebra computation, but you can think of it. But that's already something interesting, that this variety knows something about topology of the braid. And then much more subtle result, in various forms, it was proven by Webster and Williamson, and then by Anton Mellet, and then more recently in kind of most general way and kind of more precisely by Mintam Trin, is that you take this braid variety, there is some torus action on this variety, which I think I'm not going to define. So n-1 dimensional torus acts on braid variety, and you take equivariant cohomology of braid variety with respect to this torus. And then the theorem says that equivariant cohomology is isomorphic to component in HOMFLY homology of the same braid, beta W0, of top A degrees. So HOMFLY polynomial was a polynomial in A and Q. This is the quantification of this polynomial. This is also known as Khovanov-Rozansky homology. Or triply graded Khovanov-Rozansky homology. And then it has A, Q, and additional homological grading. So we just look at top A degree, we still have Q and the homological grading, and they correspond to homological degree here in homology of braid variety and the weight filtration on cohomology. So this variety is smooth, but it's non-compact, so it has interest in weight filtration.
Eugene, I'm wondering why you take this torus as n-1 instead of n. That should be the maximal torus of a GRN.
Yeah, but like, I mean, if you have all numbers the same, then this would act trivially.
I see. Okay.
So you have an action.
You're taking the quotient of the center of the GRN, right?
Yeah, exactly. So you have the torus in GLN, but like the center would act trivially. So you just. Yeah.
Yes.
And so you have the maximal torus resonance. Yeah. Exactly. And so, yeah, but like, I mean, what's interesting is that this is like really subtle. It's a smooth variety, but it's very much non-compact, and you can study its compactification, and you can study the weight filtration of the homology defined by the link. And it turns out that the weight filtration and the homological degree together are equivalent more or less to computing Khovanov-Rozansky homology of the link for this thing. So if you have never seen Khovanov-Rozansky homology before, this is probably the easiest definition of what it is for positive braids. You just take the positive braid, define this variety, compute the equivalent homology with weight filtration, and that's it. And so this torus in general is tricky. If you know that this beta W knot closes to a knot with one component, with one connected component, then actually you can check that the torus acts freely, and you just take the quotient by the torus instead of taking equivalent homology. So that's even easier. If you have a link, it's much more subtle, and you have some interest in torus, you have some interest in equivariance variables floating around, and that's what you can do. Okay. And so going back to our examples, so there is a recent beautiful paper of Pavel Galashin and Thomas Lam, when they say what happens if beta is a torus braid, so TMN. So what is a torus braid? You just take n-strand braid, draw this, so you have one strand goes around all the other strands, above all the other strands, and then you raise it into power n. This is my TMN. So take this braid and then study the corresponding variety. And then first of all, it kind of follows from what we discussed before. They proved it separately that you get an open positroid variety in the Grassmannian Mn. So this is an open subset in the Grassmannian of m-dimensional planes in n-dimensional space. And furthermore, if you want to compute the equivalent homology of the space, or equivalently by this theorem, you compute the HOMFLY homology of the torus knot, you get so-called QT Catalan number, which is a beautiful combinatorial object, which lots of people study.
You get them as what?
As a bi-graded Poincare polynomial. So again, this is a bi-graded vector space.
Hmm.
And so if you count like Q to generating function for dimensions of bi-graded components, you get the QT Catalan number. And there are lots of consequences. In particular, all homology, or equivariant homology rather, is even dimensional, and the total dimension of homology is the usual Catalan number. But maybe I'm not going to give any details here. Okay. But again, there is this beautiful connection to HOMFLY homology. There is kind of more elementary connection to HOMFLY polynomial. And there are lots of interesting examples where we know the variety. It has like very interesting meaning. For example, it's a Richardson variety or positroid variety. But it turns out to be also related to these topological things and not homology. All right. Any more questions? Good. So then I want to explain basically the proof of this result relating it to HOMFLY polynomial. And prove it, we'll need to develop this calculus of algebraic weaves, which were in the title. And specifically, this algebraic weaves will give me correspondences between different braid varieties. So here's the key lemma. So suppose that I have a braid which is non-reduced. So I have some braid word, then I have sigma I, and then I have sigma I repeated again. And then I have some other rest of the braid word. Then I can do two natural operations. So I can either replace the sigma I by one single sigma I, or I can replace the sigma I by just one and erase it completely. Both of them. And then the lemma says that actually the braid variety where I have two of this is the disjoint union of the braid variety for beta prime, where I have just one sigma I times C star, and the braid variety for beta double prime when I put just one here and then I multiplied by C. And the way they're embedded is that this guy is embedded So I have two variables here. Let's call them Z1 and Z2 on these two crossings. And then when Z1 is not equal to 0, you actually land in this variety. So you forget about Z1. Now the new variable is essentially Z2, not exactly, but related. But somehow Z1 is not equal to 0 is this C star, which happens here. So this has coordinate Z1. And here, again, if Z1 is equal to 0, instead you land here, and you have coordinate Z2 on this C. And so you break your space into two pieces. You either have x of beta prime times C star. This is an open subset of x of beta. And you have a closed complement, which is x of beta prime times C. So you can draw this as pictures, but maybe before this, let me explain what's the connection to HOMFLY polynomial. So the connection is
here. Does this look like a Hecke algebra relation?
Absolutely, it is the Hecke algebra relation. It is
okay.
Really the Hecke algebra relation, or it is topologically the Skein relation. So if you want to count points, so what happens if you count?
I see. The second one that gives the identity times Q, and the first one is the T.
Yeah, absolutely.
And then Q plus Q minus 1, right? Thank you.
Yeah, let me write it down. So I have number of points in this variety is the number of points in x of beta prime times Q minus 1. And then you just add. So in general, it's a subtle operation that you have an open subset and the closed complement. But if you just count points, you just add them. And so you have the number of points in x of beta prime times Q. And so up to some normalization, this is the same as the Skein relation. Where I relate, so I had this crossing twice, and I resolve it to either identity on the top, let's say, times Q minus 1. So this is one crossing instead of two, or I can put a negative crossing on the top. And this is just, you erase both of them and multiply by Q. And so you can interpret this decomposition as some kind of motivic version of this Hecke algebra relation or the Skein relation. And of course, like you can interpret all this directly in terms of Hecke algebra defined as cosets in Algebraic. Okay, and so basically you check that this point count satisfies the Skein relation, and then you check the base case when your beta is reduced to braid word or positive braid lift of a permutation, and that's all what you need to prove that fact about HOMFLY polynomial. Okay, so this is a very efficient way to count points. A very efficient recursion, saying that if you know how many points are here, how many points are here, then how many points are here. But of course, we're not only interested in counting points, we want to understand varieties. And so one way to encode what's going on in this lemma is to draw some pictures. So I'm saying that I have embedding of x of beta prime cross C star into x of beta, and I will draw it as this trivalent vertex where I connect two sigmas with one sigma on the bottom. And so I'm saying that this gives me a correspondence between x of beta prime and x of beta. So I can also kind of project it. Okay, I can't draw it, but I can project it to x of beta prime. In the same way, I can draw this. We won't really need right now, but if I erase both of sigma and sigma, I draw it as a cup and say that I have this cup includes embedding of x of beta double prime, whatever is here, times c to x of beta. And if that is confusing, I'll show lots of examples very soon. Okay, and if we're doing this diagrammatics, so we also have this two more types of pictures. So you have the braid relation. So the braid relation says that sigma I plus 1 sigma I is equal to sigma I plus 1 sigma I and sigma I plus 1. Okay, I don't know why it doesn't work. fine. So you can draw this as following. So every sigma I would have its own color. So let's say sigma I is always blue and sigma I plus 1 is red. And so we just trace every color and draw the 6 valence vertex. And this 6 valence vertex represents the following picture. So you have some braid, somewhere in the middle, we have this picture and this piece of braid. And then, as I explained before, the corresponding braid varieties, as algebraic varieties, are isomorphic. And so we just represent the isomorphism by this diagram. In the same way, if I and J are apart, then they commute, and the isomorphic will obviously have an isomorphism of algebraic varieties, and then we're represented by this diagram where I have a strand of color J, I have a strand of color I, they just go through each other and they don't do anything. Okay? And so, like, what is drawn on this page says that we have lots of interest in, we don't have, so here we have honest morphisms of algebraic varieties. Here we don't really have morphisms from x of beta prime to x of beta, but we rather have correspondences. So we say that we have x of beta prime, we cross C, and then we embed it in x of beta. In the same way, here we have a correspondence, x of beta prime times C embedded into x of beta. And so now we can combine these pictures, and this corresponds to combining correspondences. And we can draw lots of interesting diagrams and study lots of interesting maps and correspondences between braid varieties. So let's try to do this. Before this, so like if you combine these things, basically the same logic is like Skein relation or this recursion. You can stratify your braid variety into strata. Each stratum is C star to some power and C to some power. This is like, in some settings, it's called Deodat stratification, especially for Richardson varieties. In general, you have lots of different stratification depending on how you choose these pictures, but maybe that's not so important. What is important is that if you just use these trivalent vertices and the braid relations from here, so you either don't change your variety or you multiply it by C star for trivalent vertex, and then you embed the variety on the bottom to the variety on the top. And so by doing this, you can construct lots of interesting open charts of the form C star to some dimension in the braid variety. Okay.
So, sorry, kind of, there is this, character variety which everybody likes, who likes cluster varieties. Is it possible to cover it by this kind of?
Yes, and Anton made it as a paper. So
okay.
I mean, it's not the cover, but you like stratify it and the strata looks like this. Yes.
Okay.
So you cut, so if you have a character variety, you cut it into pieces. So you cut your surface by some arcs, and then on each arc you record the kind of Bria cell of the corresponding element of GLN, or like the type, which Bria cell it is in. So you have a lot of permutations, and then like by some arguments you can reduce it to this. Yes. So Anton made it as I mean, one very long paper and I think another paper, but like he explains precisely how do you stratify and how you do this procedure. So yes, that's very important. But in particular, yes, so in this variety, in our case, in the braid variety, you have lots of ways to basically any kind of picture where you build it from the small building blocks, where you have like either these diagrams or these diagrams or these diagrams, you can name and open top dimensional torus in the braid variety. And there will be lots of these tori, and that is, of course, very interesting. Okay. And so just terminology, so this algebraic weave that we're talking about is this diagram composed of these small pieces. And you'll see some examples. Okay. And so now let's do a few examples. So that's the first example. So I start from the braid sigma 1, sigma 2, sigma 1, sigma 1. So I just stop writing sigmas. So what can I do? So I can try to use the Skein relations in different ways. So I can either say, well, I have sigma 1, sigma 1, I can reduce it to 1, sigma 1. So that would be a trivalent vertex here. And then I do the braid relation, and I get down to 2, 1, 2. So I can say, well, I do this trivalent vertex on the right, and then I perform the braid relation, and I get sigma 2, sigma 1, sigma 2 on the bottom. So this diagram, this weave, if you like, here represents a path where you go from here to here and then to here. On the other hand, you can do the following thing. You can do the braid relation first on the first 3 letters, get 2, 1, 2, 1. Do another braid relation on 1 to 1, get 2, 2, 1, 2. And then collapse this 2, 2 to a single 2. So you do the braid relation on the first 3, then you do the braid relation, that's again this vertex here, and then you collapse 2 and 2 here, that's this red vertex here. So there are 2 different ways to get from 1 to 1, 1 down to 2, 1, 2, like this or like that. And both of these ways defines the correspondence of algebraic varieties. So this will be algebraic variety on the bottom and algebraic variety on the top, and I have a national extra C star. So I have algebraic variety on the bottom times C star and 2 algebraic variety on the top. And it turns out it's a result of computation. You don't see it immediately, but like we checked and we computed that the 2 maps or 2 correspondences are actually isomorphic. And so in this case, it doesn't matter if you go this way or if you go this way, you get exactly the same piece of the big braid variety. And so in particular, we can have lots of pictures, but whenever we see this piece of a picture, we can replace it by this piece, and somehow from the viewpoint of this correspondences between braid varieties, you get the same thing. Now to the homological relations, so what Jan mentioned before. So we can start from the longest element of S4 and write all possible reduced expressions for it. There will be lots of them, I guess 20 something. I don't know how many are here, but they're all listed here. And you can go from the top one through the left down to the bottom. So let me try to do a few steps. So I have 1, 2, 3, 1, 2, 1. So 1 is black, 2 is red, and 3 is green. Then first of all, I swap 1 and 3. That's drawn here. Then I do the braid relation here. I get 2, 1, 2, 3, 2, 1. Then I do another braid relation here. So I get 2, 3, 2. It becomes 3 to 3 over here. I don't know if you can see my cursor. And then I can swap 1 and 3 here, and I can swap 1 and 3 there. That's what I do. So I get 2, 3, 1, 2, 1, 3. Then on the next step, I have another braid relation over here. So I get 2, 3, 2, 1, 2, 3. And then finally, I have a braid relation on the left. So this is 3 to 3, 1 to 3. And so that is, so this diagram on the left just represents a path in the set of all possible braid words for 1 to 3, 1 to 1 on the left. And then the right diagram represents the path on the right in exactly the same way. And so the homological relation says that, yeah, these 2 diagrams represent, so every step we don't introduce any additional C stars, we just have isomorphisms of algebraic varieties, but the left isomorphism and the right isomorphism are actually the same. So if you go around the cycle, you have an automorphism of your braid variety, but this automorphism is trivial. And so you get back, if you do the full cycle, you get a trivial automorphism, and there is no interesting kind of monodromy here. And so the reason why this is important is that various people, starting from Zimolodchikov and I guess Marian Shachman and then Elias Williamson, they proved that if you just use the braid relations, if you don't do anything else, then you have lots of isomorphisms, but only cycles, like this is the only relation that you need to check. So you have, if you have a more complicated braid, it could have lots of different presentations and lots of different braid words for the same braid. So you can have a complicated graph like this, but the only cycles in this graph of this type. So in this sense, so going back to this question at the beginning, so every edge in this picture is an isomorphism of algebraic varieties. And in fact, because there is no, like, the total automorphism around is trivial, this means that all these isomorphisms are canonical. It doesn't matter how I go from here to here or how I go this way. Okay, so this explains why this is canonically isomorphic. And if you don't check this a priori, you don't know. There is a slightly different argument of the lean for this in slightly different setup, but yeah, that's true. So that is a true state. But somehow the most interesting thing, and much easier than this or than this, you can look at this diagram. So you have sigma 1, sigma 1, sigma 1. Let me write more. And I can't write it. I don't know why. So sigma 1, sigma 1, sigma 1. Then you merge these two sigma 1s and get sigma 1 and sigma 1. And then you merge them again and get sigma 1. Or you do it in the other order. These two diagrams are not the same. So they represent different maps from the diagram on the bottom times C star to the diagram on the top. Okay. So these correspondences will be x of sigma 1 cross C star squared to x of sigma 1 cubed. And I claim that these are actually two different maps. And we can compute it because, well, we know what is the variety for sigma 1 cubed. That is this thing. 1 plus z1 z2 is not equal to 0. That's our complement to hyperbola. And we can look at two toric charts in it. So one is when z1 is not equal to 0, and that's this picture. So when z1 is not equal to 0, looks like this in the chart, but you can say, well, z1 is not equal to 0. You can draw a trivalent vertex here and continue. Or z2 is not equal to 0. And then you have a different chart, and they just are two different charts. So they are two open subsets in this variety, but they are different, and the coordinates in this tori are different, and you can study the relation between these two coordinates. And so this brings us back to this question of cluster variety. So this is a situation which is very typical in the study of cluster varieties, that you have a variety, you have lots of different tori. Each torus has some coordinates, and then change of coordinates is given by so-called cluster mutation. And so in this case, the change of coordinates is given by cluster mutation, and so you recover the cluster structure on this variety. That's why I said it was A1 cluster variety. And so in general, then the conjecture is that the braid variety is always a cluster variety. And all these diagrams or weaves, they give us lots of tori inside the cluster variety. And so they are actually cluster charts. And Gao, Shen, and Wang recently proved that this is actually true for the braids which contain W0 as a prefix. But in general, it's a bit more subtle. And that's definitely expected, but it's still a conjecture, and lots of people are still working on this. And let me just mention here that it's still a conjecture, for example, that open Richardson variety is a cluster variety. So if, and it's a hard question how to find explicit cluster coordinates on the open Richardson variety. So if one would solve this conjecture immediately, this would give you cluster coordinates on the Richardson variety. So this is not obvious at all somehow. And it's not easy, but it's interesting that somehow this kind of easy discussion, when we just like kind of look at this version of Skein relation and try to kind of combine them, it leads us naturally to cluster variety. And I think I just wanna, in remaining 5 minutes, let me just finish with this big example which illustrates everything which I said so far. And I just want you all to look at this example. So what is drawn here? So I have this braid word, sigma 1, sigma 2, sigma 1, sigma 2, sigma 1, sigma 2, sigma 1, long braid word on 3 strands. And you can study all possible ways to simplify this using just, again, 1, 1, 2, 1 or 2, 2, 2, 2 and braid relations. So for example, if I go here, so I'm saying, well, I do a braid relation on the leftmost 3 letters. I get 2, 1, 2, and I don't change the rest. Then I merge this 2, 2, and I get down to here. Then I again do a braid relation and do something like this. And then I continue doing this. So now I merge this 2, and then I get 2, then I merge this 2 and get another 2. Here I don't merge actually, sorry. So here I do the braid relation over here and get 2, 1, 2, and then I have 3 2s, and then I actually have a choice. So when I'm here, so I have a choice of either doing this or doing that. So I first kind of merge the first 2 or first merge the last 2, and this represents these 2 pictures here. Either I have 2, 2, 1, 2 and 2, 2, 1, 2. So the braid words are the same, but the way we get there is different because I choose which ones to merge. And then I merge them again and get 2, 1, 2. So this path over here, I don't know, sorry. And that path, they both represent these 2 different trees. Okay, and so basically, so each path from the top to bottom gives me either this weave diagram or it gives me a map. So if I have a path top to bottom, so this is the same thing as the map or open embedding of x of sigma 2, sigma 1, sigma 2 times c star cube, I think. Let's see. So this has length 3. This has length 7. So I need to add 4 letters. So I think it will be 4. Inside x of sigma 1, sigma 2, sigma 1, sigma 2, sigma 1, sigma 2, sigma 1. And this is the braid variety we're interested in. And again, at every step, we either do nothing, we don't change the variety, or we multiply it by addition C star and embed. And so every path gives you such an open embedding. This is actually a point. So it's just open embedding of C star to the 4 into this big thing, or it's a torus inside this big braid variety. And there are probably thousands of paths here, I don't know, hundreds of paths here, which we can study. And the point is that there are lots of cycles in this graph. So if I look at the path along this way or along some other way, if the 2 paths are related by white phase relations, the 2 paths different by white phase gives the same embedding. And so the same torus inside this big braid variety. And that was checked like similarly to that example with 1, 1 to 1 that I explained before. But I have these yellow squares, and yellow squares are actually very different because I said that this is different from this. So yellow squares correspond to mutations. I'm sorry, super slow. Anyway, yellow squares, they do give you different embeddings, and these different embeddings are related by mutations. And so in particular here, you can ask like how many paths you have. Yeah, I said I have no idea, actually, maybe several hundred. But how many different equivalence classes of paths do you have? if you allow to change a path by yellow face and don't change any by white face, and this doesn't change anything. There are only 5 equivalence classes of path up to this. And so there are 5 different interesting tori in this picture. And there are 5 different toric charts. Try it right again. No, I don't know. Sorry, my computer is very slow. And so there are 5 different toric charts, and this is actually a cluster variety of type A2, which does have 5 cluster charts. So let's try no. I'm sorry. No. I'll stop share and reshare again. I'm almost done, so I'm just want to write on this page. Nope. Okay, anyway, so yeah, I think I've said this in words. So there are 5 equivalence classes of path. They correspond to 5 tori in the braid varieties. And it's interesting in general. And so in general, this conjecture about cluster structure says that like you can draw all these possible diagrams. There are lots of them. You can ask which diagram give the same torus and different torus, and we have some tools to study this. And you can ask like, are there more tori? So in general, like you can have infinitely many cluster tori, and you can try to draw like really weird diagrams. And I think there is a lot of lots of interesting things to say here, but I'll stop. It's my computer for you to work.
Yeah, your computer told you to stop.
Yeah.
Yeah, well, thank you very much. So, well, are there any questions?
Yeah, so I'm a bit confused with this picture. So there are other ways to simplify the word, right? So why don't you apply braid relation on like 2nd, 3rd, and 4th letter, and then simplify to ones, right?
Yes. So here, like the only braid relation that I use are when I have 1 to 1, and it goes to 2, 1, 2. So I always go in one direction. Okay.
And you only
so like
multiple twos, right? Not multiple.
No. You can kill multiples of ones. I think you see this. Maybe you don't see it here actually. Anyway, but like you can feel it. So here you have the octagon, right? So here you have eight things here. If you do all possible braid relations, you'll have some stuff in the middle of this octagon face, and you'll have in fact like 5 pentagons. So 4 pentagons inside the octagon, and like all of them will give you relations, and you have even more paths, which I didn't include in the picture. That's right. So you can do more of this, but in fact they kind of, we know what happens. So we know how many. So in this phase,
so it's not going to give any new charts. That's why
it's not going to give you new charts for sure. It's like, so you have this kind of, I mean, in this case, it really looks like a skeleton of polyhedron by some reason which we don't really understand. So this polyhedron has, I think, the square chart, like the white squares, the yellow squares, and the octagon. I think that's all what you see here, really. And so whenever you see the octagon, you can fill it in with more stuff. And there will be like 4 pentagons inside each octagon, and you can study them. But anyway, so you have more paths. You're totally right. But somehow they don't give you new charts, and they don't give you information, so we don't put it here.
All right.
Yeah, but like, I mean, the way to draw this diagram is just to go always from 1 to 1 to 2, 1, 2, and not the other way around. Yes.
More questions? All right, so I have few questions, but kind of maybe a little bit tangential. It's about maybe generalizations or relation to what you've done. So kind of minor question, if you replace usual braid group by the affine version, will you get something interesting?
Yeah, that's a good question. I don't know, but I would be very interested to know. So this is related to the linguistic varieties, and people have been studying affine the linguistic varieties, and that's probably related, but I don't know how to do this, but I would love to know by many reasons. Also related question is like you can do it. So this is all type A braid group. You can do it in other types, and somehow theoretically you can. Like practically, I don't know how to write matrices, but I think it follows from like general results of Lustig that you can write matrices. It just will be more complicated, and the Hecke relations will be more complicated.
Okay, and another question, it's sort of about the work which of Fok and Goncharov, which I, of course, forgot since I heard about it. It's from 2005. It's some construction, they called it amalgamation of cluster X varieties. And basically they start, if I remember correctly, from some combinatorial data, something like braid semigroup, or they also introduce some they call Hecke semigroup, and starting with elementary cluster varieties, they build more complicated, I mean, which some kind of, I mean, morally, I don't know, maybe not just morally, it resembles what you said. You start from some simple kind of braid varieties and build more complicated, and conjecturally you say that starting with simple cluster varieties, you build more complicated cluster varieties. If they indeed all clusters. So it's, yeah. So I don't know. I mean, if you know that paper, you maybe you tell me immediately. What's
I don't really know that paper. I know that like there is kind of, there are some technical subtleties here, but like for some class of braids, which is smaller than what we do, I think it's related to what they're doing, and it's definitely related to this Gauss and Venn paper. So Gauss and Venn, they use amalgamation. And so I can say something, or I can try to say something. This one.
Yeah, and I think kind of the last of couple of questions. It's about this Zamolodchik of tetrahedra.
Sorry, let me try to reshare. Okay, sorry. Let me try to.
Yeah. No, it's kind of question. You see, you presented this braid variety story just as kind of part of algebraic geometry, but on the flag variety, there is a Poisson structure coming from the Poisson-Lie structure on the group SLN. And I'm just wondering whether they are, at least these double Breuer cells, this kind of intersections.
Double Breuer cells are part of this.
They are Poisson with respect to this structure. And so why? I mean, I met the Zamolodchikov equation in my work long ago, like I believe like 30 years ago, because it was maybe in 92. And it was related to the representation theory of quantized coordinate rings of Poisson-Lie groups. And we wrote a paper with Kazhdan. Maybe I even can find, I think it was published in Guildfund seminars proceedings. But anyway, we found a way to construct solutions to Zamolodchikov tetrahedra equations. And the idea was very much similar. So the point, the idea kind of, we didn't have kind of complicated braid varieties. We had, I believe, just Schubert cells. But the point was that if you have a Poisson-Lie group SLN, it can be quantized, deformed with respect to parameters, say Q. So now it's a algebra of functions on the quantum group. You can study its representations. And these representations, they parameterized by, I would say, by braids in your language. Because the condition that the square of simple reflection equal to 1 didn't play any role, just a braid relation. And so the fact was that if you have a word in the braid group, then to this word you can assign an irreducible representation of this non-commutative algebra. Okay. And the theorem was, which actually I proved, that the result up to an isomorphism does not depend on the it depends only on the braid in your language. But in fact, this representation is a tensor product of representations corresponding to these simple reflections, to sigma i's. Yeah. All right. Now, if you take, for example, like the group SL3, take the longest element, W0, and decompose it in 2 different ways, you get a unique up to an isomorphism representation, but this isomorphism between the two, very much similarly to your view. Yeah, it satisfies the homologic of tetrahedral equation. I think we proved it using some results of Khovanov and Voevodsky on 2 categories, but it can be proven directly. So I'm just curious whether that whole stuff might be related to or upgraded to your story. Was at least in the special case.
Yeah, that's very interesting. So you have a representation for every braid. Yeah, I should definitely look at that.
Yeah. Okay. And yeah, and you mentioned it's another question at the last one. You mentioned the relation to this Khovanov and so on, and you mentioned the special case of torus knots.
Yeah.
And there are, of course, million other ways to see HOMFLY in this torus knot, like Oblomkov and Schende's story.
Yeah.
Yeah, and what's the relation? Is there any relation between that generating function and anything?
Generating function is the same. So you can ask what's the relation between the spaces, and that's a very good question. And there are
I meant the spaces, but I was afraid.
So this space is always smooth but non-compact. Oblomkov and Schende space is usually, I mean, it's always compact if it is a knot, but it's almost never smooth. And so here you have this weight filtration. There you have so-called perverse filtration, and the expectation, or like, I mean, in this case, it's a consequence of just explicit computation that the two results are the same. So you can take homology of this braid variety with the weight filtration. You can take homology of their variety with perverse filtration. Both give you correct answer for Khovanov-Rozansky homology.
Do you mean that there is a version of P equal W?
Yes. Yeah. So there is a conjecture that there is a version of P is equal to W here, and like one would hope that there is some kind of non-abelian Hodge correspondence here as well, but that's not known. And there are lots of interesting questions. But I think the expectation is that, for example, if you take an algebraic braid, so take a plane curve singularity, take the corresponding braid, define the braid variety. So braid variety again is smooth and non-compact, or you can take their like compactified Jacobian of this curve that's compact but not smooth, and study the relation between homologies, or maybe a relation between spaces, I don't know, but like numerically they relate like homologies match. But the way we know this is just like for torus knots, we know how to compute everything explicitly.
By the way, kind of it's a question rather educational. Well, if I'd like to see it on the Hilbert schemes of C square of the plane side, what should I do? should I construct some sheaf on
Yeah.
it? And
Yes, that's also true. So like both of these are supposed to correspond to a sheaf on the Hilbert scheme of points on the plane, but that is like very different story from.
and this sheaf can be constructed explicitly, or it's kind of abstract. Some
There are various ways to do this. Like one way is to say that Hilbert scheme is proj of some explicit algebra, and then just construct a graded module over that graded algebra. Another way is like this series of papers of Oblomkov and Rozansky. So they have some kind of really complicated matrix factorizations over the Hilbert scheme, or like really complicated space above it, and then you project down to the Hilbert scheme and you get the sheaf. So,
but there is no kind of intuitively clear geometric.
No, there is no geometric construction as far as I know. No.
Yeah. Okay. All right. Thank you. More questions? Well,
Yes, I do. Sorry,
okay.
yeah. I have to unmute my.
You
Try
jumped
to unmute my microphone.
Yeah. Okay.
And so you mentioned, actually earlier you mentioned about the generalization to other. I mean this variety definition works for any reductive groups without any problem. The question is how to describe this braid relations or how things move.
No, braid relations, like, I mean, the question is how to write explicit matrices. So like how to parameterize explicitly like all these Borel cells, I guess. And like how to make this change of variables that I mentioned in the beginning. So you have this change of variables from like Z1, Z2, Z3 to Z3, Z2 minus Z1, Z3, and Z3. And that's a non-trivial thing. So I think like from general principles, you know that there is a change of variables, but I don't think anyone wrote it explicitly. But
yeah,
I might be wrong.
In cases of a symplectic group, for example, that's a type type C var group, and just between the long root and the non-simple root, and that probably it's not too bad to write, because in more general case, that all what you need to do is just fix to one Borel subgroup and take the matrix is the image of your important group, but you conjugate it for the different roots. You conjugate by the var group representative and mapping to the, and then you intersect with that Borel subgroup. Am I right?
Yeah, more or less.
Oh, here, the question, you somewhere somehow understood that you said something with the Soergel bimodule, the relation.
Yeah, the relation to Soergel bimodules is that you can compactify this space. So this space is non-compact. So like it's related to Bot-Samuelson, like it's an open subset of Bot-Samuelson variety. And you can compactify it to close Bot-Samuelson variety and like study this compactification. And that is the relation to Soergel bimodules, basically.
I see.
So Soergel bimodules, you can think of them as like equivalent to homology of Bot-Samuelson varieties and things related to.
And equivalent with respect to maximal torus.
Yes, that's right. So in this case, yeah, you can compactify all these braid varieties and you get something also nice and smooth. And the compactification would actually depend on the braid word. So it's slightly more subtle. So this variety is like a braid invariant. Compactification will not be a braid invariant, but you can still define it. And that's kind of direct relation to the. That's right.
And so that compactification might also give something about the category, or?
Yeah, I mean, it's a way to prove this thing, for example, in HOMFLY homology, because you're saying that, yeah, in Hecke category, you can write like all these things.
Okay.
I don't know how to say this, but in any case, like you can compute the homology of the space by saying that you compactify, and then you take homology of the total space, and then you have homology of these divisors at infinity, and then you have kind of big complex built out of this. And that really matches how you compute the Khovanov-Rozansky homology using Soergel bimodules.
Okay. Well, thank you, Eugene. That's a very interesting talk.
Yeah, thank you. Thanks for inviting.
Okay, well, thank you very much. If there are no more questions, so thanks. And I ask you to send just a final version of your notes with all these
Okay.
remarks.
Yeah, okay. Yeah, sorry for computer problems, but yeah.
It's no problem. Okay, thank you. And this is
Right.
it.